Hey guys, so I just wanted to put this video together because it should hopefully give you some background on the next task. Well, maybe not the next task, but the task after that. That's actually a pretty big one that we want to get done this semester. Um, so I don't know your level of familiarity with diodes. I'm pretty sure most of you have not taken ECE 311, which is the electronics course, and that's where you learn about a lot of these diodes. Oh, by the way, the quality probably is horrible on this, so also my bad on that. And I'll probably be pausing every now and then because I didn't actually rehearse this or write something down. But that being said, so diodes. So this is the schematic symbol for a diode. It's a really thick pen. It's better. So you can see that there's basically two ends. One is called the anode and one is called the cathode, and that's important because this device has polarity. So like a resistor doesn't have any polarity. Whether you plug it in one way or the other, it doesn't matter. Some capacitors don't have polarity, some do, but diodes will always have a polarity, at least from what I understand. They always will have polarity. That's what makes them useful. So for a diode, it's basically an element that only allows current to flow in one way. And that's generally what it does. There are exceptions to this, but more or less that's what a diode is for. And so basically in a diode like this, current will be allowed to flow from left to right, but not from right to left. So it can flow from the anode to the cathode, but not the other way around. And so down here I have anode must be at a greater voltage or potential than cathode for the diode to conduct. And when the diode is in this state where you have a higher voltage on this left side than on this right side, then that's called forward biased. So when the diode is forward biased, that means current can flow. So for example, if I have a configuration like this, I have 5 volts right here, and initially, right when I plug this in, I'll have 5 volts here, and more or less I'll have 0 volts here, and so 5 and 0, this diode will conduct current and allow current to flow. This isn't going to remain at 0 volts, but just initially when you're plugging it in, that's how you have to kind of think about it. And so effectively an ideal diode will turn into a short circuit when it is forward biased. So basically just a straight wire you can draw taking the place of that diode. And then on the other hand, reverse biased is obviously the other way around. So if I have the diode plugged in this way, plugged in reverse from the last image, I have a higher voltage here on the cathode, and I don't actually remember cathode and anode, so that's why I have to scroll back up to look at it. But I have a higher voltage here on the cathode than on the anode, so no current is going to be able to flow through here, and effectively I can treat this diode as an open circuit in that case. So nothing's going to flow through this circuit. So in reality, a diode does not behave ideally, like I just was talking about. So a diode always has some voltage drop when it's forward biased, so it's not actually going to be a short circuit like I had drawn right here. It's actually going to maintain some sort of voltage drop. And the voltage drop is characteristic of that specific diode. So depending on the material of the diode, whether it's silicon or I don't know what they use, germanium maybe, something like that, it can have, a 0.7 volt drop, 0.3 volt drop, 0.5. There's a bunch of different, it can have a different drop based on different characteristics. And although we're going to treat this as constant, so for example, I have a diode and I'm telling you it has 0.7 volt voltage drop, this is actually not necessarily constant. In reality, you have something that's like this, which I will draw it probably very poorly, and it will look, I believe they draw something like this, where this is the current I through the diode, and this is the voltage across the diode. So right here I would have an asymptote, and maybe this is 0.7 volts. or something. So basically, as you apply more forward biased voltage across the diode, it will allow more and more current to conduct. But that diode will not allow itself to have a higher voltage than whatever that rating is. So if I tell you 0.7 volts, that means that diode, no matter what voltage you put across it, will never go higher than 0.7 volts. Once it reaches 0.7, it will stay at 0.7. Hope that made sense. So let's see. So yeah, as I have it drawn in here, if I have that same circuit I showed you before, actually instead of this diode becoming just a straight wire, it's going to act as a 0.7 volt drop. And so I have 5 volts here minus 0.7, so I'm actually going to have 4.3 volts across this resistor here, across the remaining circuit. So as I mentioned, when a diode is forward biased, it will maintain its voltage, whatever the specific diode's rating is. So here I have 2 examples. This is the one that I just showed you before, 5 volts, and then I would have a 0.7 volt drop here, and I'm left with 4.3 across this resistor. In this case, if I have 50 volts here, still this diode is going to be forward biased. It's still going to maintain that 0.7 volt voltage drop. And so now here, at this point, I have 49.3 volts, which are going across this resistor. So power through a diode is calculated like, power through anything else. Power equals IV. And so a lot of the time with the diode, there's different ones. You can use power equals I squared R. You can use V squared over R. But resistance typically isn't really talked about too much in a diode. So usually, since we have like a voltage rating for the diode, in the cases I've given you 0.7, we would be able to use that for the voltage. And then using that voltage, if you're able to analyze the circuit and figure out how much current your circuit pulls, then you can figure out the power dissipated by the diode. So an example, for example, in this circuit, if I have 5 volts here, 0.7 across the diode, I have 4.3 volts across this resistor. Now, the current through this circuit is the same everywhere, right? Because everything's in series. So I can figure out the current going through this resistor by using current is equal to voltage divided by resistance. So I can take this 4.3 volts, divide it by the resistance, which I have right here, and that will give me my current I through the circuit. And then the voltage across that diode is 0.7. So the current going through the diode times its voltage is going to give you the power. I just used an arbitrary resistance here, so there's not actually value in this problem. But that's how you do the calculation. So the diode is actually dissipating power, so that's something to keep in mind. So the reason I'm talking about these diodes is because we're going to have to design a hot swap circuit, which I'll show you in a minute why we might want to use diodes for that. So the idea of hot swapping is we want to switch 2 batteries out when one that we're using is low, obviously so that it doesn't die, so we don't damage the battery, and so we can run our system properly. So one way of doing this, and the first way that comes to most people's minds, is to just put 2 batteries in parallel. So I say, okay, if I have, maybe I have V2, this battery here, plugged in, and V1 is not yet. But V2 is getting drained, it's really low, so I say, okay, I'm going to plug in V1, and then I'll take out V2. And it seems like, yeah, maybe it should work. The issue with that is that these 2 batteries will have different voltages, right? If this one's drained, 3.7 volts per cell is typical of like a healthy LiPo battery, which is what we're using. So maybe I'll say 3.6 volts is low. 3.6 volts per cell times the 6 cells that we have gives you, I don't know, what is that, 18 point, I just used 21.7 here. I know that's not the answer to what I just said, but for example, okay, let's consider V1 as our low battery, and it has 21.7 volts across it, whereas our new battery, V2, is at 25.2 volts. So if I redraw this circuit, in reality, a battery, it does have this voltage within it, but there's also an internal resistance within a battery. And so basically that internal resistance can lead to you not actually seeing this full voltage that you have right here. So for example, if I use a voltmeter and I probe each end of a battery, positive and the negative terminal, I'll see 21.7 volts for this battery. And I see that because a voltmeter has what we call infinite impedance. It basically has, it's like an open circuit. Even though you're touching two probes, one on each end, you're not really completing any circuit. No current is being allowed to flow because of how a voltmeter is designed. So because of that, all I see is that 21.7 volts. However, when you actually model a battery, it looks more like this, where you have your voltage here. So I can say 21.7 volts. And within that battery, I also have some internal resistance. And so whenever I'm actually pulling current from this battery, I will have 21.7 volts minus the voltage dropped across the internal resistance of the battery, which would be equal to whatever current I'm pulling multiplied by the internal resistance. And so actually, if I'm using this and I'm using some current from this battery, and then I measure how much voltage I see from the negative to the positive terminal, I won't see 21.7. I'll see 21.7 minus the voltage dropped across this internal resistance. So in this case, that's important because if I just plug in a second battery in parallel with this first one, what's going to happen is this battery across here, let's say before anything is plugged in, nothing's plugged in at all, and we have 21.7 volts from here to here. And then initially I plug this one in, and so I have 0 volts here, and I have 25.2 volts up here. Well, that's not possible for me to have 21.7 volts and 25.2 volts. So this battery is going to begin charging the lower voltage battery, but also because the maximum voltage I can have across this battery here is 21.7 volts, that's the voltage that I'm going to see all along this top line, which means if I'm seeing 21.7 volts right here, then I must have 25.2 volts minus some voltage across this internal resistance is going to be equal to 21.7 volts. And so I believe I did a calculation somewhere right here. So this actually right here and this number, 3.5 volts, is going to be the voltage that has to be dropped across this internal resistance. So the battery is basically going to pull as much current as necessary to drop 3.5 volts across this resistance right here, so that you have the same voltage across both these batteries. So in order for us to have a 3.5 volt voltage drop across this resistance, and this actually, the internal resistance for a LiPo battery I looked up is roughly 6 milliohms per cell, and we have a 6-cell battery, so that means we have 36 milliohm internal resistance. So to get 3.5 volts across 36 milliohms of resistance, you can just do current is equal to voltage over resistance, and that gives you 97.22 amps. So just connecting these two together in parallel, you're going to have 97.22 amps pulled from this battery to charge this battery here, and that's a lot. Honestly, something would probably like fry before then, or maybe not. Maybe our batteries can handle that. But my point is that's bad. Stuff will get really hot, at least. And when stuff gets hot, resistance goes up, and then you actually dissipate more power, which is a different topic. But that's one called thermal runaway, if you guys are interested in that. But I don't know too much about that. So basically, that's a lot of amps. Power dissipated in the battery, then we can calculate power is equal to voltage squared over resistance, right? So if I have 3.5 volts dropped across that internal resistance, I square it, divide by the internal resistance itself, I get 340 watts dissipated in here. So that's all wasted energy that's that's, like I said, dissipated across this resistance. So that's not like it's being used to charge this battery. That's just totally wasted. And that is a lot of watts. That's a ton of power. Since we have so much current coming, a lot of current is a lot of power. So basically, this is a bad idea. Don't do this. A better idea is to use diodes. So actually, if we have our circuit like this, where we have each battery and then a diode in series with them, then if we assume the same sort of thing, so one of these batteries, V1, is 25.2 volts and the other one's 21.7, let's assume for this example that they're both forward bias diodes, so they're both allowing these batteries to conduct current, basically. So let me scroll down to here. If I have 25.2 volts across this battery right here, then that means if this diode is forward biased, I will have, we'll say, a 0.7 volt drop. So 25.2 minus 0.7. Oh, I didn't use, okay, I used 0.5 for this example. Like I said, it's different for different diodes. So we'll say I have a 0.5 voltage drop across these diodes. So that would leave me with 24.7 volts up here. And same for this battery, except 21.7 volts at this point minus 0.5 is going to give me 21.2 volts. As I mentioned before, you can't have two different voltages on the same wire, theoretically, right? So what's actually going to happen, since this battery right here, if it's forward biased, it provides 24.7 volts. So let's consider 21.7 volts being present along this whole wire. So at this point, 24.7. On this end, we only have 21.7. So this diode actually would have a higher voltage here than it would down here, which would make this guy reverse biased. And if I consider, well, yeah, basically that's the idea here. So this diode, it's not possible for both these two to be forward biased. Since this guy has such a higher potential, it's going to prevent this diode from becoming forward biased. Therefore, you're going to have no current at all coming from this battery, and this branch is effectively an open circuit. So more or less, this, you can act as if this branch doesn't even exist now. So let's see. Yeah, so again, this is what we'll see, 24.7 volts across here, which means this guy is not conducting current. We have no current in here, and just current will be pulled directly from this battery to the robot. So let's see. So yeah, so now since this guy's effectively disconnected, now we can just unplug it, there's no problems, and we don't have all that power being wasted, drained from the internal resistance of the battery itself. The one problem, I guess, I mean, there's always a trade-off. The one trade-off that you make, now we can hot swap, but the thing is, while we are conducting current through here, I didn't actually add this in, but maybe I'll draw it out. So while our robot is operating, maybe we're pulling, I'm just going to pick a number, I don't know, 25 amps is what all of our robot components need to operate, we'll say. Okay, so we need 25 amps here, which means we're going to pull 25 amps from this V1 battery right here, right? So 25 amps going through here. Well, there's going to be some power dissipated by this diode. So we're going to have this diode, if we stick with 0.5 volts, which is actually closer to the type of diodes that we'll probably use. They're called Schottky diodes. But if we have 0.5 volts across this guy, and we have 25 amps, power equals IV, right? So we're going to have 0.5, this is actually really hard to do with the mouse, times 25 amps, and that's going to give us 12.5 watts across that guy. But actually, maybe a better way to do it. So I did talk about this voltage rating. I may have said before that resistance is not really used with diodes, but that's actually not necessarily true. In ECE 311, it's not really used for diodes, but in real world, it actually can be useful. So let's forget this for now. Right? I showed you this 0.5 volts is not actually constant. It's sort of a curve. So depending, it's a range from 0 volts up to this threshold, right? So there's also another curve, which I'm not exactly sure how it looks, but based on the current you're pulling through a diode, its internal resistance will be some certain value, or I should just say its resistance rather. So let's say that the resistance is 0.3 milliohms or something like that. This should always show on the data sheet. So I'll say resistance is 0.3 milliohms and I need to pull 25 amps. So I'll use something like P equals I squared R. Off the top of my head, I can't really do that, but well, 0.3 of 0.3, 0.09 times 1/100th of this, something like 2.5 watts, and that sounds closer to a correct value. So yeah, this guy probably should be used in that case, this resistance and this current. But basically what I'm getting at, you don't have to remember all these formulas or anything, but having that diode there is dissipating power that currently we are not wasting because we don't have a diode in there. So there is that trade-off, but overall this will let us hot swap, and so it's probably worth it. Also having that diode there, pretend that I didn't add this new battery in yet, pretend I just got rid of that. If I have a 21.7 volt battery with a 0.5 volt drop, that's going to give me 21.2 volts at this point. That voltage may not be enough to satisfy certain things that have to run at maybe 24 volts. Usually there's a range. If it's a 24 volt item, maybe it can go from 22 volt all the way up to 28 or something, and it can function properly. So maybe 21.7 was just barely cutting it. But if I drop another 5 across this diode, 21.2, maybe it's going to have some issues since that's less than this threshold. So yeah, just some stuff to think about. Let me know if you have any questions about anything that I talked about, guys.